This eLesson is about comparing the energy systems. So you can see here that we've got the three energy systems. We've got the ATP-PC system, anaerobic glycolysis, and the aerobic system. We've got aerobic glycolysis and aerobic lipolysis. So the ATP-PC system, the fuel used is phosphate creatine, and we can see here that the rate that it can resynthesize ATP is very, very quickly. The problem being is that it has a low capacity. It only produces this much ATP. When we compare it with anaerobic glycolysis, the fuel used is glucose. It is fast at resynthesizing ATP, but you can see it's not quite as fast as the ATP-PC system. It, however, has a greater capacity than the ATP-PC system, producing a little bit more ATP. If you compare those two to the aerobic system, you can see that the aerobic system itself produces so much more ATP. Therefore, it has the greatest capacity to produce ATP, but the problem being that it is the slowest. Okay, it has the slowest rate. We look at the fuel source for the aerobic system. So for the first 90 minutes, we're looking at the breakdown of glycogen, so glucose as a fuel source. And then after about the 90-minute mark, we switch to using fatty acids, so fats as the fuel source after 90 minutes. Remember, glycolysis is the breakdown of glycogen, lipolysis is the breakdown of fatty acids. So these three systems do not ever function independently or at one time. They always work together, and this is known as interplay. So all three systems are activated at the start of exercise, and their relevant contribution is essentially determined by the intensity and the duration of exercise. So depending on how long it is and how intense the exercise is, determines whether we use predominantly the ATP-PC, predominantly the anaerobic system, anaerobic glycolysis, or whether the aerobic energy system is the dominant contributor to ATP resynthesis. So depending on mainly the intensity and the duration of exercise will determine which energy system is the dominant one. Obviously also whether oxygen is present or not, and the depletion of chemical and food fuels during exercise will also play a part. Here this graph shows at rest that the dominant energy system is the aerobic, okay, contributing to about 95, I would say about 90-95% of energy, whereas the anaerobic and ATP-PC system are still contributing to ATP resynthesis, but to a smaller degree. If you take the 800 meter, for example, the aerobic system is still the dominant energy system. However, there is still a contribution made to ATP resynthesis via anaerobic glycolysis and the ATP-PC system. During a marathon, you can see that the aerobic system is still the dominant, and again, there is still a contribution made by the anaerobic glycolysis and the ATP-PC system. Here is just another graph, okay, which was also used in one of the exams. So at the start of exercise, we can see that the ATP-PC system is the major contributor to ATP resynthesis. However, as the duration progresses, so as time increases, you can see that it decreases its contribution to ATP resynthesis, and anaerobic glycolysis is now contributing during the 10-second to 30-second mark. All right. The white line represents the aerobic energy system. So you can see at the start of exercise, it does make a small contribution to ATP resynthesis. However, it becomes the dominant energy system, all right, at about the 1 to 2 minute mark. So very few sports rely on a single energy system. Most events use a combination of energy systems, and the body doesn't suddenly change from one energy system to another. All three are contributing to ATP resynthesis. However, depending on the duration and the intensity of exercise will determine which one is the dominant one. So you've seen this graph many times before. What it is the oxygen consumption during exercise. So down the bottom we've got an increase in exercise time. Here exercise stops, and here is where exercise starts. So at the start of exercise, you know that the oxygen supply and demand are not equal. The body is demanding more oxygen than we can supply, and therefore we see this oxygen deficit. When the body has adapted to those changes, so increased respiratory rate, increased tidal volume, increased heart rate, increased stroke volume, increased cardiac output and ventilation, and the demand is equal to the supply, that's when we see a steady state occur. So when we're talking about oxygen deficit, it's a temporary shortage of oxygen in the cells, which occurs at the start of exercise when the body's demand for oxygen exceeds supply. The respiratory and cardiovascular system can't act quick enough to satisfy the demand for oxygen, and therefore the energy required must be obtained from its anaerobic energy systems, including the ATP-PC system and anaerobic glycolysis, and they don't rely on oxygen. So whenever we see oxygen deficit, it's clear to say that the anaerobic systems are the main contributor to ATP resynthesis. Oxygen consumption rises rapidly at the start of exercise for the first few minutes until the sufficient oxygen is taken up, transported, and then utilised to meet exercise demands. Once this occurs, it's referred to as steady state, where oxygen supply equals oxygen demand, and virtually all of the ATP that's required to maintain the current exercise intensity is being supplied aerobically. So wherever we see a plateau in the graph, it's fair to say that the aerobic system is the dominant energy system. When the body is in steady state, this is where lactate can be broken down and removed and then converted back into glycogen in the liver. And remember that this process is called gluconeogenesis. So on any oxygen consumption graph, so oxygen consumption, steady state will be presented by plateaus of unchanging oxygen demand. So any plateau here, the blue line, is where the athlete has reached a steady state. So heart rate has leveled off, your respiratory rate has leveled off because oxygen, so there's no need to increase them because oxygen supply is now equal to demand. Periods of oxygen deficit will be represented by steep lines representing oxygen uptake, or if you're looking at a bar graph, it'll be large increases in the height columns. So here, the red lines are oxygen deficit. Okay, so you've got steady state, oxygen deficit. Wherever there's steady state, it's clear to say that the aerobic system is the dominant energy system. And when we see oxygen deficit, all right, other than at the start of exercise, the dominant energy system is still the aerobic system. However, there is a greater contribution made by the anaerobic glycolysis system. Really important that you understand that. Okay, so let me just go back to this graph here. All right. At the start of exercise here, oxygen deficit. Major supplier of ATP is your anaerobic system, so the ATP-PC system and anaerobic glycolysis. When we hit a steady state, it's the aerobic energy system which is dominant. If here the athlete decided that they would sprint to the finish line, what you would see is a line up and increasing. All right, so that would be oxygen deficit there if the athlete sprinted to the finish line. That oxygen deficit, all right, the aerobic energy system is still the dominant energy system because the athlete has been going for more than 2 minutes. But what happens is that there's an increase in the contribution made by anaerobic glycolysis. Let's have a look at this one, this graph here. So what we've got is at the start of exercise, okay, we experience an oxygen deficit. Right, so major contributor to ATP resynthesis is your ATP-PC system and anaerobic glycolysis. We hit a steady state, right? So the aerobic system is the dominant energy system. The athlete has then increased their oxygen consumption. So they're going up a hill and maintaining the same pace, or they're just sprinting. Okay, they're increasing their intensity of exercise. So again, we see oxygen deficit. All right, and then the athlete then reaches another steady state. So here, the energy system between this part of the race is still, the dominant energy system is still the aerobic system. However, during this section here, there's a greater contribution made by anaerobic glycolysis.